Thank you, Chantal, and welcome all. And I'm just standing here in place of Ghislaine Godet, who is at the University of Paris-Saclay, and she is the chair of this panel, the research focus panel. So over to you, Ghislaine, and I'll stop the share on this slide.
Thank you. Thank you very much, Anna. And I'm very honored to act as a chair for this panel, but I just recently stepped in to replace Nathalie Sinclair from Simon Fraser University, Canada, who was finally unable to participate, but Nathalie actively prepared and inspired this panel. I was previously only the liaison member of the scientific committee of the symposium for this panel. How do computational thinking and mathematical thinking interact is a very complex issue, and maybe you have already read the abstract of the panel on the website. You can see in particular in this abstract that this issue can be perceived very differently by different stakeholders in the mathematics education discipline. So to shed light on this complex issue, the scientific committee invited panelists representing the international mathematics education research community. All these panelists are prominent mathematics education researchers involved in particular in research about computational thinking, programming in mathematics education. And moreover, their research covers all school levels from primary to university. So I will now briefly introduce them. Dr. Paul Drivers, who is professor at the Freudenthal Institute of Utrecht University Science Faculty in the Netherlands. Paul Drivers is well known for his research on the role of ICT in about the role of ICT in mathematics education. And this naturally includes computational thinking and programming. He is also this year the IPC chair for the next CCMEME conference in Budapest in next July. So we are very happy that he took time to be with us today and work in this panel. Dr. Erini Geraniu is Associate Professor of Mathematics Education at the Institute of Education, University College London, UK. And Erini is also actively involved in the next CCMEME conference, and she works also in a 4-year research project in Europe investigating programming, computational thinking, and the so-called mathematical digital competencies in the teaching of mathematics in different countries in Europe. And Dr. Elise Lockwood, who is the only one representing us physically in Brock, Associate Professor in the Department of Mathematics at Oregon State University in the US. Her research concerns more the undergraduate level. She is currently serving as a co-editor-in-chief of the International Journal of Research in Undergraduate Mathematics Education. And before becoming editor-in-chief of the journal, she published in it with her colleague Knut Morken from Oslo, a paper calling for research exploring relationship between computing and mathematical thinking at the university level. So about the program of this panel, it will combine presentations of the panelists about the historical landscape, but also about what they anticipate for the future. As you have seen in the program, the panel is presented as a research panel, but you will see that it is also closely linked with practice. The panelists will invite you to participate actively through tasks that they will propose, and they will also react to your contribution. So an important part of this panel will be on-the-spot improvisation, depending on your active contribution. So, and now we start already, and Elise will introduce the first task.
Yes, thank you so much, Ghislaine, and thank you everybody for being here. We do very much want this to be an active participation type panels. So we are going to put you all to work and ask you to engage with us in a few different ways. There are 3 questions there just to get you thinking both about your own, like your interest in CT and also your own positionality regarding these questions related to computational and mathematical thinking. We've observed that, yeah, there's lots of different perspectives that people are coming in with, lots of different starting points. And so maybe you can take about 3 minutes just to read those questions, kind of think about them on your own. And then we'll have about 3 minutes for a discussion with somebody you're sitting next to. We can move chairs a bit if you want. And then spend about 3 minutes entering some responses into the Padlet. So a little bit of just personal think time. We can help you make sure you get connected. And then I will encourage you to talk to your partners in just a couple of minutes. Okay, everybody, I'm gonna call us back to order here, if I may. Thank you so much. And so you can be thinking about those questions. We now, the plan is for Paul and then myself and then Irene to share a little bit about our perspectives and our kind of what brought us here, what we've been thinking about in terms of computational and mathematical thinking. So Paul will begin. And as we're going, you can continue to think again about the answers to these questions. You can be reflecting. You can feel free to continue to contribute to the Padlet if you'd like. But I will turn it over to Paul.
Thank you very much, Elise, for your bridging to my talk. I hope you can see my screen. So first, let me apologize for not being there and present in person. It was not feasible. I hope we can communicate this way. In this next small 15 minutes, I will try to sketch the landscape of research on computational thinking and mathematical thinking, a bit also in retrospect, and well, try to pick out some components that may be helpful for our discussion, even if I should admit they're also quite straightforward, and maybe you all know this already. So how do computational thinking and mathematical thinking interact? That's the big question. Sorry, there's something, yeah. So why do we speak about this? Well, it also emerged in the Padlet a few minutes ago, and you probably are all aware of this, because our private and professional lives are full of interactions with digital technology that are based on computations. And as future citizens and professionals, we need to be able to deal with this, and to do so requires insight into the computational processes involved. This is all very straightforward, but is it any new? Well, not really. Here you see a very old picture, I think it's the 1980s, where there's a huge round like turtle moving over a piece of paper, guided by the commands, by the instruction given by the young child on the left to make some drawings. And this is, of course, really the basic idea of computational thinking already a while ago. Is it really new? It's also not new, because we already had it in the 1980s, Seymour Pappert's Mindstorms, in which he wrote down visions of how to integrate computational thinking into everyday life was insufficiently developed. And I'm afraid that like 40 years later, it is still insufficiently developed. And Pappert's theoretical stance was one of constructionism, in which he highlights, to put it a bit bluntly, in which he highlights the importance of learning through making, through constructing, through, well, doing something that results in a specific product or effect. And this is still very much alive, even if there was a while that we didn't hear that much of it. But computational thinking really re-entered the scene by this article by Janet Wing in 2006, which I'm sure you will all know. And this led to a revival and to different definitions, because somebody in the Padlet just said, depends on what we mean by it, of course. And this is an issue because there are still quite some definitions around. To quote one by Lodi in 2020, computational problem solving, so he speaks about problem solving, not about thinking, is the formulation and solution of a problem must be expressed in a way that allows an external processing agent, a human or a machine, to carry it out. So roughly speaking, it's like translating a problem that you have in such terms, procedural or algorithmic terms, that you can outsource it to an external agent. Can be your neighbor, can be a robot, can be a device or computer language, programming language. So even if there are still a lot of definitions existing, I think this is more or less where the debate is converging to. Okay, we have definitions, and then soon in literature there appeared this view that CT is a kind of container concept which has different components. And in decomposing CT, we see lists like in this left column: abstraction, generalization, decomposition, algorithms, debugging, or similarly 2013, 2015, problem solving, abstraction, generalization, decomposition, algorithmic thinking, modularization. And of course, this is where my heart as a mathematician starts to beat, because many of these concepts, abstraction, generalization, algorithms, are really at the heart of mathematics and of mathematics education. So this is how we see the two coming together in some way. In some way, okay, but in what way? What exactly is the relationship between computational thinking and mathematical thinking? This is a topic that is getting more and more popular as a research field. And to illustrate that, I did a search in Scopus database on terms like computational thinking and mathematical thinking, education, learning, teaching. And I found 150 papers, and you see clearly an increasing graph. So definitely the topic is getting more and more researched, and it's like an emerging research field. These 150 papers were published in different types of journals, in social science journals and in computer science journals, for example. And this highlights that we are somewhere at the edge of different disciplines. It's about education, it's about computation, and we are somewhere in between. And the United States were the country that was most frequently the home of the papers that were published, as we can see here. Maybe more interestingly, if we take these 150 papers, it is nice to see where they referred to. And thanks to the software by Sébastien Groin on the bottom, I counted the papers these 150 referred to. And there you clearly see the Wing 2006 being the top one and Peppert's work being second. So clearly the two I just mentioned before form the foundations of the field and are the mostly cited ones. So an emerging field of research on the relationship between computational and mathematical thinking. But how do we see this happening? One way to investigate this relationship was through a literature-informed Delphi study, which we carried out a few years ago, to investigate what the overlap might entail if we agree that there is some relationship between. Now, in this Delphi study, we came up with this final conclusion. Again, I'm going to read it to you. Computational thinking in math education is a structured problem-solving approach in which one is able to solve and/or transfer the solving of a mathematical problem to other people or a machine. This is what we already saw. By employing thinking processes that include, and then we have these components that were mentioned, like abstraction, decomposition, algorithmic thinking, generalization. I put some in red because I find them particularly relevant. So clearly there is some common ground, but how do they exactly relate? And there are different views on this. One view is this one. It roughly says like, okay, there was somebody in the Padlet who said CT is a subset of MT, and this is reflected here. So one view is, okay, computational thinking is now very much in fashion. But what it all comes down to are fundamentals of mathematical thinking, like abstraction, generalization, So what we should do is don't follow the hype too much, but just make sure that we do good mathematics education in which computational thinking elements are embedded. That's one view. And to do so, I will show you two examples. This one was an example we used with Dutch students, 16, 17-year-olds, who were provided with a spreadsheet with data reflecting the passengers of the final journey of the Titanic. And using this data set, they were asked to answer some questions through transforming the data. And this is what we called data moves. And through these data moves, they create new variables which they investigate to solve specific problems. In this case, the example was counting the number of children in the population, in the people on board. So I guess this is mathematical thinking, but also could be labeled as computational thinking. The second example is same type of students, but this time more oriented towards science and mathematics. They were asked to explain to GeoGebra, to provide GeoGebra with commands that would allow it to draw a sheaf or a bundle of tangent lines to a specific graph. And the graph itself was not drawn, but through all these tangent lines, you can see the graph itself emerging. So this is a way to explain an agent, the agent here is GeoGebra, how to solve a specific task. So I would call this computational thinking within math education. So there's one view, but there are other views. Another view could be, okay, guys, our lives are full of devices and technology and algorithms. So computational thinking is really the inter or multi or transdisciplinary science that is at stake and that's important. And why bother too much about these old-fashioned mathematical things? Mathematics is not this isolated ivory tower. It should just be treated in function of this overarching goal of how to deal with technology and the algorithm in the society around you. So this is completely a different view, of course. And I'm curious to have your opinions because we will explore them in the second hour of this panel. This brings us to coding because algorithms need to be implemented through codes, so programming. And computational thinking and coding and programming, this relationship is also a bit vague, to be honest. Some people consider it like more or less similar and others consider it completely different and make a plea, for example, for unplugged activities. I happened to have a nice experience just a few weeks ago with mathematics teachers in a workshop. I just asked them, please explain your robot or an lion or your roommate or maybe your partner how to fill the dishwasher. And this gave rise to very interesting discussions. Of course, you have to open it, but then the first thing to do is check whether there are already some things inside. So if, and here I use an if statement, if there are some things inside, you have to check whether they are clean or dirty. If they are clean, you better take them out before. If they are dirty, they should stay. And then, of course, you start filling the dishwasher until there's nothing left to put in. So there were a lot of things that relate to computational thinking, even to algorithm, to programming, to mathematical thinking that can be addressed without any coding or programming. Programming, coding, algorithms, well, we have artificial intelligence now, which consists of algorithms that are a bit beyond of our control often if you consider machine learning. So what's the relation between these two? That's a difficult question, to be honest. As an example, when we speak about coding, we should be aware that, for example, ChatGPT does a lot of elementary coding, which is a real concern to my computer science colleagues in my faculty. For example, I asked ChatGPT, provide different Python codes for adding the numbers 1 to 100, the famous Gauss problem. And then it comes up with very nice routines or codes that are appropriate, and it also explains what the different methods are. So at least as a computer science programming educator, you need to think about these simple examples. Now, how do they relate? I didn't provide a final answer, I'm afraid. I do like the words algebra and algorithm because they both have this Arab foundation or roots. And I wonder whether we should focus math education more on algebraic thinking and computational thinking education on algorithmic thinking. And this is maybe where the two might meet. But this is just a thought for this session. Also, myself as a mathematician, I do see the value of mathematical thinking in many aspects of my life, like, for example, filling the dishwasher. It is an algorithm, it's a procedure, which comes down to dealing with tools and like outsourcing jobs. So to me, mathematical thinking and computational thinking are really very much related to themselves, but also to many daily life problems that I encounter. So in my mind, maybe my spoiled mind, because I studied mathematics, CT and MT are really very closely related, and they are worthwhile to teach, not because of the sake of having programming languages, not because of the sake of having mathematics tasks that are hard, but for the sake of being able to deal with challenges in your life. And that's in fact my very global stance on this. So to conclude, I didn't take care of the time, Ghislaine, but I hope I'm still in time. To conclude, I hope to show you that the landscape of CT in education is still quite scattered. And that makes some of us, I saw in the Padlet, a bit skeptical about it. But I hope I convinced you that CT and MT, computational and mathematical thinking, do share common ground on these important aspects like abstraction, like generalization. How to cultivate this common ground still is not yet completely clear, and we have seen some extreme different views. And there are options to explore, and in fact, probably this is the main goal of, well, at least the second part of this session.
Thank you.
So sorry for not having final answers, and thank you for your attention.
Thank you very much, Paul. And now to Elise.
Okay. Hi, everybody. So now it is my turn to share a little bit about my perspective. Can you hear me okay? Is this good? All right. Yeah, so I do just want to kind of talk about how much I appreciate all the different perspectives that are represented here, and certainly in working on the panel, we saw different viewpoints and perspectives. So I just want to share a little bit because I think that there's kind of value in seeing how the interest in computing can stem maybe from a grounding in kind of mathematics education research. So just a little bit about myself. I don't come at this as a coder or computational mathematician. So, you know, I have a PhD in math education. I'm an associate professor in the math department at Oregon State. But up until, you know, I started getting more interested in this a few years ago, really had essentially no computational background formally. Didn't program a lot growing up, didn't have very good experiences in undergraduate or graduate school, and still feel very much like a novice in the space of kind of actually engaging with coding. But because of that, I think I can kind of articulate my interest in it as hopefully being kind of authentically motivated by my work in math ed research. So my work really has focused on investigating undergraduate students' reasoning about combinatorics and counting problems. And if that sounds very narrow, it is. It's very specific, right? Kind of a niche topic, but it's really wonderful. And I appreciated, I think, something that Dr. DeSessa said last night about the joy of just seeing students learn and engaging with students learning. And that's really what I love more than anything, is watching students and helping students solve counting problems better. But for most of my career and most of that work, I did that really not considering computing whatsoever, not explicitly, not even very implicitly. Didn't think about, I mean, I knew that there were applications for discrete math in computer science, but never really drew on that. But I want to kind of describe the shift then that made me get more interested in a computational perspective. So again, this is hopefully, and I'll show this on the next slide, that my motivation to engage with computing really is driven kind of theoretically by my math education research. And so a central finding of my work in combinatorics education emphasizes the value of helping students focus on the sets of outcomes they're trying to count. All right, so if we think of a counting problem, like how many 3-digit sequences are there from the numbers 1 to 6 that have no repeated digits? Right, so that's a combinatorics problem that you might see that kids or undergraduates might try to solve. And if you were to solve this, you might employ a 3-stage process like this one, right? Where I have kind of 6 options for the first digit, right? 1 through 6 for any of those. I have 5 for the second option because I'm not repeating digits. And then for any of those, I have 4 options, right? And because the number of options at each stage are independent, I can multiply those to get 120. Maybe you recognize this as a permutation problem. It's arranging 3 objects from 6 distinct objects. And I think students can try to solve these problems without, like this, using a process, identifying a problem type. But what I really want to do is to draw students' attention to the sets of outcomes that they're counting and the structure. What is it really that I'm counting, and how does a process like this kind of generate a set of outcomes like this? And I have a model of students' combinatorial thinking is something that came out of my early work that really emphasizes the value of having students connect a counting process to the set of outcomes they're trying to count. And there's lots of reasons for this. I think it's easier to justify and to avoid that you have all of the outcomes, to not overcount. So it's kind of a foundational finding, say, of my work in combinatorics education. And so some ways to connect processes and outcomes might be to list, right? To have students engage in listing behavior. But it's not hard to see limitations of by hand listing, right? That it's hard to list 120 things by hand. It's hard even to maybe have students list, 20 or 30 things by hand. But I really still valued and wanted to think about how I could connect counting process to sets of outcomes with lots of different types of problems. And so that's when I thought, well, what if some very kind of simple Python programming could allow students to kind of encode essentially a counting process like this that would let them then immediately, instantaneously generate an entire set of outcomes, and thus reinforcing this idea that the counting process is connected to the set of outcomes, right? And so the work I've been doing more recently has been to kind of develop little modules that students might use to support their students' combinatorial reasoning via some very simple Python programming tasks. Does that make sense? Okay. So in terms of what Paul mentioned as some of these models, I think also I'm not giving just a definitive answer. I mean, I think there's a lot still to discuss. But in my work, again, my motivation is largely to support my students' mathematical and combinatorial thinking. Like that's really my goal and my motivation. But I see, for example, in that little bit of Python code with the nested for loops, the potential really to allow for some thinking about that code can simultaneously involve computational thinking and yet also involve some thinking that's going to support their combinatorial reasoning, right? So I do see these things as interacting. I think that computational thinking can exist that is not maybe inherently mathematical. I think mathematical thinking can exist that is not inherently computational, but that there is something here at the intersection, and that's, I think, kind of where I see my work and my interests living. Okay, so just a couple comments about interests in future work. Again, my main goal is to explore ways in which research on computational thinking can build upon what we already know and what we're finding about math ed research, right? That we're not going to computing because it's popular or it's kind of the next new thing, but that it really is theoretically grounded in the questions that we're trying to ask and answer to support students' mathematical thinking, in my case. And I don't know that we have to totally overhaul everything. Are there ways in which even very modest engagement with computational thinking and activity can support students' mathematical thinking? And that's what I think, for instance, my work is. We can still teach combinatorics in lots of different ways, but does some exposure to some code like that support them mathematically in some in some unique ways that the not having a computer is missing. I want to say too, I've benefited from engagement with computationally minded researchers in other disciplines. This is with physics ed researchers, computer science ed researchers, science ed researchers. And I think there's a lot of potential there, not only within the math ed community, but beyond to learn and to grow together. And I wonder if there is a future where computational and mathematical thinking can reflexively develop and grow. Okay, so that is all I have for my comments. Thank you.
Thank you. Thank you very much, Elise. And now I invite Irini to contribute.
Hi, everyone. It's lovely to virtually meet everyone, and my apologies for not physically being there with you. It was out of my own hands, I'm afraid. So I'm going to start off by sharing a question that I keep asking myself for the last few years, and one that I have been asked by colleagues too, and which you have already been asked to answer in the Padlet already. Why is computational thinking important in mathematics education and mathematics education research? And why does it seem to be appearing in discussions within the mathematics education community and beyond? My own research interests regarding computational thinking focus on investigating mathematics educators and mathematics teachers' views and perceptions on computational thinking and its impact on mathematical learning, and also on identifying strategies for promoting computational thinking and its integration in mathematics teaching and learning. In order to look at these two research foci, I had to look into what computational thinking is. And here I will only share a few quotes out of the many, some of which were mentioned by Paul as well earlier. And I will pause just for 10 seconds to give you the chance to skim read this, because I know that it's a quite populated slide. As you notice, I have highlighted keywords in these definitions, such as competency, new digital age competency, thought processes, practices, a range of practices. And reflecting on these definitions, we start thinking about whether computational thinking is indeed a competency and how it relates to mathematical thinking. Paul shared with us his thoughts, and Elise as well, on this matter, and looked at these two being separate, but also having an intersection, but also being a subset of each other. In Sanz et al.'s research, computational thinking was synonymous to doing mathematics using digital tools. So my question is, are computational thinking and mathematical thinking only linked when doing mathematics using digital technologies? And is it that everyone thinks when we ask them about computational thinking? My recent work with Jeremy Hodgen, also from UCL, indicated that some mathematics educators struggle to articulate what the relationship between computational thinking and mathematics is, and as a result, viewed computational thinking as closely tied to computers and other digital tools. Carrying out this research work with mathematics educators prompted me to start thinking about the relationship between mathematical knowledge, thinking, competency, and where computational thinking fits in. Having in mind that computational thinking was perceived in the literature as a competency, as I mentioned earlier, I reflected on definitions regarding mathematical competence to identify potential links. In fact, I wondered whether there is a link between computational thinking and mathematical digital competency, which is a construct developed recently by myself and a colleague from Denmark, Uffe Jungqvist. So Uffe and I argued that when solving a mathematical problem using a digital tool, having mathematical competency and mathematical knowledge, and on the other hand, having digital competency and knowledge of the digital tool equips you to solve the problem. So in a sense, we said that mathematical digital competency is the interplay of mathematical competency and digital competency. And subsequently, we developed an MDC framework, as we called it, where we said that a student possesses MDC if they display the following three characteristics. So the first one, being able to engage in a techno-mathematical discourse. So knowing the tool, knowing how to communicate with the tool, but also knowing the mathematical language and how this is represented in the tool itself. That means that you are fluent and you have techno-mathematical discourse, right? The second element is being aware of which tool to apply when you're trying to solve a mathematical problem, for example, and being aware what the tool can do and cannot do, so that you can use it effectively to solve the problem at hand. The third one is being able to use digital technologies reflectively in problem solving and when learning mathematics. Going back to my work with Jeremy Hodgen on mathematics educators' views on computational thinking, I want to share some reflections regarding our discussions with one of the mathematics educators we interviewed for our research. In those interviews, we asked mathematics educators to bring a mathematical task involving the use of any digital tool that they are familiar with. So we had some using GeoGebra, some using Excel, and some of them using Scratch, which is the one that I'm going to talk about now. So the activity was designed to enable students to investigate the modeling of an infectious disease such as COVID from a scientific and mathematical perspective. The modeling, as you can see here, a snapshot from the Scratch activity, involved mathematics, and therefore that mathematics educator argued that the case enabled him to articulate his own views and competency relating to mathematics and computational thinking. So he used Scratch to design this simple model of the effect of different factors: movement, hand washing, the transmission rate, and healthcare capacity on infection and death rates. The environment allowed students to change these factors to explore their effects. The image, as you can see here, showcases the computational modeling of this real-life problem. So inspired by these interviews, it became clear to us that possessing computational thinking is a competency. And in fact, we argued that it's a mathematical digital competency. And we adapted the MDC framework. So in this table here, you can see that in bold, there are three elements of the mathematical digital competency that considers computational thinking practices. So the first one is about still to engage in a techno-mathematical, but also computational discourse. The second one, being aware of which tool to apply within the given situation and the different tools' capabilities and limitations, so as to start thinking and interacting with these tools while considering the benefits and limitations. And the third one, being able to use digital technology reflectively in problem solving and when learning mathematics, considering and applying computational modeling, such as the one that we just saw in that diagram being designed and developed in Scratch. So I would like to conclude with the argument that computational thinking may indeed be a mathematical digital competency, an interplay that involves mathematical thinking knowledge and competency, and with digital knowledge and competency. Thank you very much for your attention.
Thank you very much, Irene. So now we will go back to your answers on the Padlet to the free question, and I will invite the panelists to react to what was written on the Padlet. I don't know if you want to react to question by question, starting with question A. Question A was more descriptive. I noticed that several people asked for a definition and said that it was not easy to answer to the question without a definition, but it was a choice from you to start working without the definition to see if there are different interpretations among the public before contributing and presenting these possibilities, these first reflections. So it's as you prefer. Do you want to start with saying something about the question A, or do we just notice the variety of levels of themes that were mentioned by the colleagues about question A? Perhaps, yes, Paul?
Yes, thank you, Ghislaine. I found it interesting that on the question 1, of course, we had very limited time to look at Padlet, but in the left column, there were quite some examples, more than I had expected, of concrete mathematical topics, exponentials, logarithms, whatever, probability. And I find it interesting because it suggests that there is a quite diverse range of topics that you can use to address these basic things from mathematical and computational thinking. And to me, this really makes sense. So maybe it's not a matter of topic, it's maybe a matter of the way in which you teach this topic through paying attention to computational thinking and mathematical thinking skills. So that was just my first impression for the first question.
I think the kind of definitional confusion perhaps, or some of the issues with how can we, I think, progress in talking about these together as communities without having, I think, pinned down definitions. And I do think that, I know there have been whole workshops dedicated to try to define and understand computational thinking. And I think, speaking for myself, I feel like there are just, particular, it's like phenomena that I observe in the students that I feel like do reflect something that I think is at the heart and core of computational thinking, even if I can't define it. And I feel like still at that place of being exploratory and trying to understand the phenomenon. So I feel like there's a balance between just not engaging because we can't define it perfectly yet. And yet I think there's still work that we can and should be doing to try to understand even what the phenomenon is that we're trying to explore, and that we're a little bit in that space now of still needing to investigate more. And I think that's where the conversations that we're having, this type of dialogue, these types of just events, I think can be really productive. So I think thinking carefully about how to proceed, even with some of the ambiguity that is just at us, around us, as part of this endeavor. So just wanted to say that.
Thank you, Elise. And Irini, you raised your hand.
Yeah, I just wanted to say that I agree with the comments that everyone is making, that it's very difficult to define it. And if somebody comes and asks me now to define it, I would struggle, because it is so many things. And also what I kept thinking, especially since Paul made this historical account from 30, 40 years ago and where we are now, is that how we, at our age, and how we grew up, our own education at that age, it's very, very different to how the kids currently at school and how they're thinking, because they have computing as part of their educational system, as well as mathematics. But the problem that I see currently is that they don't talk to each other, these two disciplines. So if you talk to a mathematics teacher, how they would introduce maybe a programming in the lesson will be completely different to how a computing teacher would introduce it at school level. And whether they would bring in the maths and how they would model the maths and what discussions they would have. So I think that one thing that I would say is that maybe having more conversations between the different disciplines that they use coding, they use programming, and also that they're using mathematical problem solving, so that we can find common ground and be in a better place to define what computational thinking is and how it closely relates to mathematical thinking. Thank you.
Thank you, Irini. So yeah, it's a difficult exercise for the panelists to naturally had a very limited time to read the question, but it was a choice also for the organization, and they will go on improvising about the answers. So maybe there were so many very rich answers to question B. So maybe you pick up some of the answer. I think that some of the answers were quite positive, in a positive stance about what it affords the students to do more problem. They can solve more problems. There is this idea of more conceptual and less procedural exercises. Also the idea of interaction, depends the interaction between who and who. So Paul, you want to react?
Yes, it is interesting to see in the second and the third column of the Padlets some big differences. Some see it as well, this is not clear enough. We need to be more sure. Others say, okay, there's a lot of potential. We need to do more rich problems, or in a more societal view, we need to like, or kind of like political, I would say, agenda in concerning equity and equal access. And so I was surprised by the big variety in the second and the third column. And in fact, I would be interested if we were having enough time to have all these people speak out the background of their input in the Padlet. But this, of course, this is not feasible. But the diversity is surprising to me.
Thank you, Paul. Elise, Irini, do you want to add something?
No, I would just say that it takes a lot of time to develop computational thinking, in my view. And so I would give anyone trying to develop that for their students, for at any age, quite some time to be able to engage with it and find the links and bridge the mathematical thinking with computational thinking. And as I keep coming back here, that it's not well defined, not really well developed, a long way to go. All these comments I think I relate with, and it's very, very interesting that computational thinking is not a new term. And so I agree that there is a little bit more research work to be done to see how this computational thinking can become part of our maths lessons and part of maths education as a whole. Thank you.
Ghislaine, I can just make one other comment, which is I think that those questions related to considering different populations is intentional, and I think again, I personally have been thinking about this a lot from a research perspective, and this will come up some I think in the second hour. But what are implications for math education research and for the professional practice of being a math ed researcher? What about from policymakers or from political perspectives? And so as we think about computing, computational thinking and activity and how it progresses to thinking about coordinating all of these different kind of stakeholders with lots of different perspectives and motivations, I think is an interesting thing to consider.
Sorry, can I just add one more thing that I just noticed one of the comments that talks about equity. And I just want to touch on that because it's very true. I mean, different students have different access to technology, different training. I mean, some teachers have training, they know they have their CT-like skills and to teach mathematics with computational thinking embedded. So I think it's a crucial issue to address in the future about equity in accessing technology, training for teachers and mathematics educators, so that we can talk about CT becoming more evident in mathematics education in general.
Thank you very much, Irini. So I think that for this moment of discussion about the answers to the three first question, it's We can stop here now.
So we're going to start the next hour is going to be a couple of vignettes that we're going to look at. So I'm going to go ahead and put up the QR code and the bit.ly link for the first vignette, just so we can get that going, but we'll come back in just a couple of minutes.
I mean, I can introduce it. It's just, so this is one scenario, as we call it, the vignette one, and it's about the adventure travel list problem. And it's about 2040 and what the maths teacher sets as a homework to a year 9 class. So your task is to read for 5 minutes the scenario, and then for 5 minutes in your pair to be able to discuss it, and then be prepared to answer the general questions in the given Padlet, which you can find at the very end of the scenario, at the end of the vignette, but also on the Padlet itself. So I think we need to do very tight timekeeping to make sure that we don't run out of time. So if we say that the first 5 minutes of reading the vignette start now, and hopefully everyone has been able to access the bit.ly link and see the vignette. Thank you.
So keep reading silently, or as you start to get done reading it, feel free to discuss with somebody sitting next to you. I put up now the vignette or the Padlet QR in bit.ly, which is separate from the vignette bit.ly. And it's the same Padlet actually for both vignettes we're going to do, so just be aware. But if you need me to go to the other screen, I can.
So maybe now we should move to the second vignette.
Yep. Okay, everybody, I am going to thank you so much for your thoughts. You can continue. And again, in case it wasn't clear, this was meant to just get some conversation going, get reactions. So we appreciate your feedback. We have a second vignette. So same kind of deal. We also have a couple of paper copies of this. This is a little bit broader in nature, so I'll keep this up for a little bit. Same thing, read it. Please do discuss it. If you haven't talked with anybody yet, please make an effort to talk to somebody. And then in a little bit, I'll put the next link, and actually, it's the same Padlet. It's the same Padlet, so you can just go to the same Padlet link.
The panelists will now start by reacting to these contributions, and then we will try to have a more general discussion, perhaps. So maybe Irini, sorry, you.
Thank you.
Take the first one.
Thank you. Yes, Elise, could you please move to the next slide after this one, please? Thank you. And first of all, thank you very much for engaging with this activity. And it was great for me to read your views in the Padlet. And what also put a smile on my face was the comments regarding the context of the mathematical problem and whether traveling will be feasible, for example, in 2040, because it's always a case, you know, when you give a mathematical problem, quite a few of us just get stuck in terms of the context. I want to say that the vignette is an adaptation of the traveling salesman problem that some of you spotted, as I noticed in one of the comments. And it is a shortened scenario to ensure that we had time to discuss and comment within the time constraints in our panel. What I really hope was that at least some of you were surprised to find out at the end that Sophia was an artificial intelligence tutor that had computational thinking, and her aim was to support Mark with developing computational thinking. And I agree that Sophia could be programmed to have a lengthier conversation with Mark before giving up the code. Also, it may be interesting to say at this point that the code offered by Sophia is a code ChatGPT produced when I asked how a 15-year-old student would answer the traveling salesman problem using a programming code. And that's what ChatGPT came up with, which is similar to a code that ChatGPT produced when I asked how to solve this problem, which is interesting to see that it's programmed in that way. As you can see in this slide that is shared, I have highlighted relevant elements from the Mathematical Digital Competency Framework to indicate where there is some evidence of Mark and Sophia showcasing an interplay between computational mathematical thinking and competencies based on that framework. And therefore, I just want to conclude by saying that I hope that I got you to start thinking about whether we can consider computational thinking as a mathematical digital competency. And I can see that not all of you are convinced, but I just hope that I prompted you to start thinking about it. And maybe with more evidence, it could be something that we are all convinced with. Thank you so much. Thank you. Now I'm going to hand over to Elise. Thank you.
Yes, I think, Paul, if you want to discuss. I also.
Yeah, thank you very much. Well, if I look at the Padlet, there were some people who were even bored by the scenario. And of course, we presented two quite extreme cases, but this was meant to highlight the different ways we can go. And for sure, the truth might be somewhere in the middle. But still, on the one hand, if we need everybody to be able to deal with life around them, and on the other hand, we need some specialists who are able to know what's happening in artificial intelligence. We still have quite a spectrum to cover, quite a range to cover. And I guess this is going to be an educational challenge, which is like illustrated in the two parts of the vignettes. Another comment, which also refers to vignette 1, I guess. In vignette 1, the role of the teacher was taken over by the chatbots. In vignette 2, we raised the question, how about math education as a field, as a scientific field? Will it, well, deserve its proper position, or will it be like merged and integrated in other fields? That's also just an interesting perspective from us as professional researchers. On the slide, that was done beforehand, of course. We kind of summarized some views that, of course, we see the value of both MT and CT, but don't know how exactly, whether and how they should be integrated. And therefore, we sketched these two perspectives, the pure and isolated option on MT and the more embedded real-life applied option. And decisions that we will take about on this, not us, but policymakers, I guess, in the next decade, they are important because some people already raise this equity issue or the digital divide. This is a concern indeed, and we purposely put the opposite, or sketch the opposite directions to highlight this. But this is definitely an issue that will be discussed over the next decade, I guess. Thank you.
Thank you, Paul. So, Elise, do you want to add something or about vignette 2, or do you want to start taking live reactions?
Sure. Yeah, you can be thinking. I think we would welcome kind of comments where we only have 10 minutes left, and so I'll open the floor if people just have comments overall. I'll just, I think, reiterate what Paul had to say. I appreciate the comments about issues of accessibility and equity, and I think that those are things that we want to be thinking about. And I think, yeah, like Paul said, as math ed researchers, thinking about what does it look like to grow interdisciplinarily and to collaborate, and what does the profession of being a math ed researcher look like in the coming decades. But I think with that, we are happy to open the floor a little bit. I know you've been responding on the Padlet. There's no pressure here. I can bring the microphone around. If anybody, yeah, we would just welcome any comments, any questions. And if there are none, that's also okay, but wanted to give people a chance to respond if you'd like.
I think from the first half of the panel session, I kept thinking of some comments that Eric Mueller gave us yesterday in the working group. And I don't know if you like to talk about that grammar, because I just think your thoughts are so interesting, Eric.
Thank you. I'm looking from I'm a mathematician, so I'm looking at it from a rather narrow point of view. And my point of view is really the development of programming for learning of mathematics. And as you know, we have a number of courses at Brock in the math department, which has focused on that since the year 2000. And the way that I see programming is as if you think of the traditional pillar of mathematics as you go through high school, what you have is you have your algebra. And then once you have your algebra, you now have a sort of unit, which some people may call a tool, but it really is something, it's become the grammar for the calculus. And then when they have that understanding of calculus, they now move up, let's say, to analysis, and the calculus now becomes the grammar for that. And I see the programming within mathematics as forming a different pillar. The programming now becomes one of the grammars. Once you have that, you have one of the grammars for discrete mathematics, for modeling, for those areas of mathematics, which you can approach in a new way through computation. And that becomes the grammar for me for this area of mathematics. And notice that this area of mathematics takes things from the traditional mathematics and presents them in a different way. So it's a different view of mathematics for me than I had through the traditional what I call classical approach that we had through. But the point was raised yesterday where we can use a computer science course for developing that understanding in mathematics. And at Brock, we tried that and it didn't work. And my view was that the students were spending far too much time on the grammar rather than the environment of the mathematics, where they were really interested in learning. And the future math teachers follow that route also, where they can look at mathematics in a different way. So you're using a different grammar. So it's a different pillar, as the mathematicians in Europe have said that this is a different pillar of mathematics.
Thank you so much, Eric. And I see, Paul, you had your hand raised.
Yeah, thank you. Unfortunately, I didn't have the opportunity to attend your workshop yesterday, Eric. But to me, it seems that you're speaking about relatively high-level mathematics and high-level students. What to me is another interesting topic, and I would be happy to hear the opinions in the audience, is what to do with the low or average achieving students who are in the same world as we are, right? And have to deal with the same developments. And that's a different topic compared to the one that Eric was addressing, I think, but to me, highly relevant.
I'm going to
Okay.
engage in debate here, Paul, because I think I've had students, and I'm talking low level, end of primary school, who were low achievers in mathematics. And when we started giving them logo programming and doing dynamic geometry, suddenly they were excelling. So it was because they were a different kind of thinker, and they weren't doing well in school in traditional mathematics. And when we gave them these tools, they were able to express themselves in a way that was maybe more according to how their brains worked, and they suddenly excelled. So I don't think what Eric was talking about is only for higher level students or, university or high school. I think the ideas that he was talking about are applicable also at lower levels. That's just my view. Anyone else wants to? Okay, yes. I tried to go there so the camera would pick me up, but if you can state your name.
Hi, my name is Kendi Ladipo from Humber College, Toronto. I read the last paragraph of the vignette 2, and what immediately jumps to me is equity issue, because this is a content creation that is isolating the bottom 95%, only selecting the 5%, and those are the ones that have the opportunity. The only people that have the chance to become engineers and scientific leaders. So when we are designing our curriculum that integrates CT, we should think of how we can give the opportunity to every learner to achieve their potential. And this may include just giving a variety of different forms of achieving their goal. Some may be able to, like, as you said, some may light up and understand better when they see the actual demonstration through activity in the classroom.
Yeah, that's perfect. Thank you for that comment. And certainly I think hopefully we can think about how, and again, yeah, that last bit is extreme, right? That and to think what can we be doing now to engage students and to hopefully promote more equity and accessibility across the curriculum for more students. So yeah, appreciate that. Yeah. Oh, we can.
Okay, here's good.
Yeah.
I don't really know. So I appreciate the 2 speculative fiction that you've presented. I don't know where it's intentional, but even though there's some context, they're a bit acontextual. And I see both of them as being more evolutionary rather than revolutionary. So for example, in the first vignette, it's 2040 and we're setting problems around visiting 5 different places in the world. I wondered about, are we still doing this sort of travel in 2040? Did we survive the climate collapse and the attendant climate chaos? Which also comes up in the second one, right? With pervasive computation, there's energy inequities aligned with that. And so there's lots of really interesting things, I think, with these 2. So I do appreciate that. I wanted to point that out. And then the one we were talking about in the back a bit was the way we had to give a lot of trust to the AI and to the data. So, is the distance data provided in that matrix trustworthy? So, right, so it's not even about whether the programming is trustworthy, but is the actual data itself trustworthy? And does that really matter? So does it matter mathematically, practically, if you're actually making the trip, and consequentially on a a global level? If you did plan to make 5 airplane trips or 10 airplane trips in the year 2040.
Thank you for that.
Thank
I don't know.
you.
Yeah.
Yeah. So do we take another question, or should we close here maybe?
Are there any questions from people online, like Marisol, and I think Celia was on? Any questions from the people online? I don't see any more questions here, Ghislaine.
Okay, good. Thank you very much. So, and I think that maybe at least you can put this final slides just, and I will just invite the panelists to have a few words, say some kind of take-home message I would like to transmit to the participants. So maybe we start with Paul.
Thank you, Ghislaine. Yeah, well, of course, a concluding remark is difficult, but my strong feeling is that in mathematical thinking, there's so much that is important, not only for mathematics, but also for acting as a human in society and in the world. And computational thinking is very nicely pinpointing out how this interferes with technology and society and technological developments. So I really think it's important to think about MT&CT and especially not only just for the gifted people or the gifted students, but for everybody because, well, these equity issues, they play a role, as was mentioned in the panel. Thank you.
Thank you, Paul. So perhaps Erini?
Yes, thank you, Ghislaine. What I want to say is that I don't think that I need more research to convince myself, and I hope other maths educators as well, that computational thinking is a powerful way of thinking, and in fact, a 21st century competency. I think there's more research needed and more work to be done in order to integrate it effectively into maths education. And I do take all the points about equity because there needs to be system changes, so that we have better training for educators, for teachers that want to promote computational thinking in mathematics education, but also there are infrastructure needs so that we can ensure that everyone has access to technology, everyone has access to what they need to be able to be computational thinking competent. Let me just say that. So thank you ever so much. Thank you. I'm just going to stop there.
Thank you, Erini. Elise?
Yes, I will just conclude by saying again, I think there's value in having these types of conversations. I think there's a lot to learn. I think there are phenomena that each of us are observing in our students, in our teaching, in our work. And there's a lot to do still to unpack some of that. And I think we're just together jointly making very incremental steps based on what our own kind of passions and backgrounds and interests are. And so I'm just really welcoming the conversations, the discourse, and I'm appreciative of the chance to be here and talk with you all. So thank you.
Thank you.
Thank you, Elise. So I think we can now thank all the panelists again for their contributions. So